The sound comes first, a deep, metallic grinding, slow, deliberate, echoing through a tunnel that did not exist a few hours earlier. Steel teeth, each one nearly half a meter wide, rotate forward at a speed so controlled it almost feels unnatural. Around them, the air is thick with dust and heat. The temperature inside the machine's forward chamber can reach over 40 degrees Celsius, even in cold environments. Hydraulic cylinders, some longer than a small car, push with thousands of tons of force, pressing the cutter head into solid rock. And then the rock moves, not explosively, not dramatically, but steadily, relentlessly, a few centimeters at a time. This is the tunnel boring machine, often abbreviated as TBM. A machine so large that in some cases, its diameter exceeds 15 meters, wide enough to carve out a full highway underground. Its total length can stretch beyond 100 meters, with trailing support systems carrying conveyor belts, ventilation ducts, electrical systems, and crews of workers operating in synchronized coordination. In modern presentations, the machine is often shown as a triumph of engineering precision, a perfect circle cut through the earth, clean, efficient, predictable. The narrative is familiar. Before machines like this, tunnels were dug slowly, dangerously by hand. Workers used picks, explosives, and brute force. Progress was measured in meters per week. Accidents were frequent. Collapses were common. Entire projects could take decades. Then came the machine, and everything changed. With the tunnel boring machine, the story goes, excavation became faster, safer, and more controlled. Projects that once required thousands of laborers could now be managed by smaller, specialized teams. The machine stabilized the tunnel walls as it advanced. It reduced the need for constant blasting. It transformed underground construction from something chaotic into something engineered. This is how the story is usually told. In engineering textbooks, the TBM is introduced as a solution to the unpredictability of geology. In museums of science and technology, scale models display its massive cutter head, often polished and clean, surrounded by diagrams explaining its components: shield, grippers, thrust system, segment erector. The complexity is emphasized, but the tone is clear. This machine represents control. Control over rock, control over space, control over time. In documentaries, the visuals reinforce the same idea. A rotating cutter head slicing through stone, conveyor belts smoothly carrying away debris, workers in helmets standing at a safe distance, monitoring systems through digital panels. The environment appears organized, structured, almost calm, and the conclusion is always implied. Machines like this did not just build tunnels. They built modern infrastructure, subways beneath cities, railways through mountains, water systems crossing entire regions. They made it possible to connect places that were once separated by geography itself. They accelerated transportation. They supported economic growth. They turned engineering into something scalable. Productivity increased, risk decreased, society advanced. At least that is the version most people recognize. It is repeated in educational materials, reinforced in industry publications, embedded in the way large infrastructure projects are presented to the public. The machine becomes more than a tool. It becomes a symbol of progress moving forward, quite literally, through the earth. But even within this familiar story, certain details remain strangely quiet. For example, the machine does not simply cut rock. It grinds, fractures, compresses, and reshapes it under immense pressure. The forces involved are not gentle. They are extreme. The cutter head alone can weigh over 200 tons, rotating continuously against material that is often harder than steel itself. The energy required to sustain this motion is enormous, and the environment inside the machine is not as controlled as it appears from the outside. The noise levels can exceed 100 decibels. Communication between workers often relies on hand signals or headsets designed to function in constant vibration. The air must be continuously ventilated to remove dust and heat. Water is injected to suppress debris, turning parts of the operation into a mixture of mud and slurry. Even the idea of safety is more complex than it sounds, because while the machine reduces certain types of risk, like uncontrolled blasting, it introduces others. Risks that are tied directly to its scale, its power, and its continuous operation. But these aspects are rarely central to the main narrative. They appear in technical documents, in engineering reports, in maintenance logs, but not often in the simplified story of progress. Instead, the emphasis remains on what the machine made possible. Faster tunnels, larger projects, greater efficiency. And so, the tunnel boring machine becomes something almost inevitable in hindsight. Of course it was built. Of course it improved everything. Of course it represents advancement. But if this machine represented progress, why are some of the most physically demanding, technically complex, and potentially dangerous aspects of its operation almost never explained in the story itself? At first, the machine seems consistent. Everything about it suggests control. The cutter head rotates at a fixed speed, often between 1 to 3 revolutions per minute. The thrust system advances the machine forward in measured increments, sometimes just a few centimeters per cycle. Sensors monitor pressure, torque, temperature, alignment. On paper, it is a closed system. Inputs go in, outputs come out. Progress is linear. But when you begin to look at actual project records, the pattern becomes less stable, because the machine does not move through a uniform material. It moves through geology, and geology does not behave like a controlled environment. In some sections, the rock is dense and predictable, hard granite stable enough to support the tunnel face. The machine advances slowly but steadily. Wear on the cutter tools is manageable. Progress can be measured and forecasted. Then, without warning, everything changes. The rock fractures, a fault line appears, water seeps in, or pressure builds behind the tunnel face. In these moments, the same machine, designed for precision, begins to behave differently. The torque spikes, the cutter head slows, hydraulic systems strain to maintain forward force. Inside the chamber, the temperature rises further as friction increases, and sometimes, the machine stops completely, not because it failed, but because the environment no longer matches the assumptions built into its design. This is where the narrative begins to feel less straightforward, because while productivity increased overall, interruptions also became part of the system. In some tunneling projects, machines that were expected to advance 10 to 15 meters per day slowed to less than 1 meter under difficult geological conditions. Entire operations paused for days, even weeks, to stabilize the ground, repair cutter tools, or manage water inflow. And these pauses were not minor inconveniences. They changed the rhythm of the project. They required workers to enter parts of the machine that were never meant to be routine workspaces. To replace cutter discs at the front of the machine, crews often had to work in confined areas under high-pressure conditions. In certain types of TBMs, especially those operating below the water table, this meant entering pressurized chambers where air pressure could exceed 3 bars. The purpose was to prevent water and soil from collapsing into the tunnel. But the effect on workers was significant. Time inside these chambers had to be strictly limited. Decompression procedures were required when exiting. The process resembled conditions more commonly associated with deep-sea diving than with construction work. And yet, this aspect is rarely part of the simplified story. Another detail begins to appear when looking at maintenance records. The cutter tools, those massive steel discs at the front, do not last indefinitely. In abrasive rock, a single cutter can wear down after just a few hundred meters of tunneling. Replacing them is not a quick operation. It can take hours, sometimes longer. And during that time, the entire machine is effectively idle. But the system around it does not stop. Ventilation continues, pumps continue, Monitoring systems remain active. Energy consumption persists even without forward movement. So while the machine is often described as increasing efficiency, the reality includes periods where efficiency drops sharply, not due to human error, but due to material limits. And then there is the question of scale. The larger the machine, the greater its capacity, but also the greater the consequences when something goes wrong. A cutter head over 15 meters in diameter concentrates enormous forces at the tunnel face. If alignment shifts even slightly, the stress distribution across the cutting surface changes. This can lead to uneven wear, increased vibration, and in extreme cases, structural damage to components that are difficult to access. Repairing such damage is not immediate. It involves halting progress, bringing in specialized crews, sometimes even partially dismantling sections of the machine underground. In these moments, the image of continuous forward movement no longer holds. Instead, the machine becomes something that advances, pauses, adapts, and sometimes struggles. Even the working environment begins to complicate the picture. Despite ventilation systems, fine dust particles remain in the air. Moisture from injected water mixes with excavated material, creating slippery surfaces. Noise levels remain high enough to require constant hearing protection. And the sense of enclosure, working inside a steel structure, deep underground, often hundreds of meters below the surface, adds a psychological dimension that is rarely mentioned. None of these details contradict the idea that tunnel boring machines increased productivity, but they do introduce a different texture to that progress, a texture that includes friction, interruption, adaptation, and uncertainty. Because the machine does not simply impose its design onto the earth, it negotiates with it, and in that negotiation, the outcomes are not always as smooth as the diagrams suggest. Which leads to a quieter question. If these interruptions, risks, and constraints appear consistently in technical records, why do they remain so peripheral in the way the history of tunneling machines is usually told? At this point, the story begins to separate into two versions. One is familiar. The other is harder to see. In the familiar version, the tunnel boring machine represents a turning point, a clean transition from uncertainty to control, from manual labor to mechanized precision, from risk to safety. It is often described in broad terms. Machines replaced dangerous work. Automation reduced human exposure. Engineering solved the unpredictability of underground construction. And in a general sense, none of these statements are entirely false. But when compared to technical records and project documentation, the picture becomes less stable. Because the machine did not remove uncertainty, it reorganized it. Take, for example, the idea that tunnel boring machines made tunneling safer. In many engineering summaries, accident rates are discussed in aggregate. A reduction in catastrophic collapses, fewer large-scale explosions, more controlled excavation. But these summaries often group together different types of risk. They emphasize what decreased. Less often, they detail what replaced it. Inside technical reports, a different set of concerns appears repeatedly. Localized failures at the cutter head, unexpected pressure changes in slurry systems, mechanical faults in rotating components operating under extreme load. Each of these carries its own form of risk, not always dramatic, but persistent. In some documented cases, cutter head interventions required workers to enter confined spaces where rotating parts had to be manually secured. Lockout procedures were followed. Systems were isolated. And yet, the margin for error remained small. The machine did not eliminate danger. It concentrated it into more specialized situations, and these situations required a different type of expertise. Another commonly repeated idea is that the machine accelerated progress in a linear way. More machine, more speed, more output. But historical data from tunneling projects rarely follows such a simple curve. Instead, progress appears uneven. There are phases of rapid advancement, 10 meters per day, sometimes more in favorable conditions, then periods of near standstill, not because of poor planning, but because the interaction between machine and geology introduced variables that could not be fully predicted in advance. In engineering logs, these phases are described in detail. cutter wear rates, torque fluctuations, ground settlement measurements, water ingress levels. Each variable influences the others. Each adjustment creates new conditions. The machine does not operate in isolation. It is part of a system that includes material, environment, and human decision-making. And this system behaves in ways that are not easily summarized. Yet, in popular narratives, this complexity is often compressed into a single direction: forward. Another simplification appears in how labor is described. The familiar version suggests that machines reduce the need for human effort. And in terms of raw numbers, this is often true. Fewer workers are required compared to earlier tunneling methods. But the nature of the work changes. Instead of large crews performing repetitive tasks, smaller teams operate within a highly technical environment, monitoring systems, maintaining equipment, intervening when conditions shift. And these interventions can be physically demanding. Replacing a cutter disc, for example, is not a passive task. The discs themselves can weigh over 100 kilograms. They are installed at the front of the machine, often in positions that are difficult to access. The space is confined. The surfaces are uneven. The air may be pressurized. The work requires precision and time. In this sense, the machine does not remove labor. It redistributes it from visible continuous effort to intermittent, high-intensity tasks that occur under specific conditions. This redistribution is rarely emphasized in simplified accounts because it does not align as neatly with the idea of machines liberating workers from physical strain. There is also the question of timing. In many narratives, the introduction of tunnel boring machines is presented as a clear shift, a moment where one method replaced another. But historical adoption was not instantaneous. Early TBMs faced limitations. They struggled in mixed ground conditions. They required extensive support systems. They were expensive to build, transport, and assemble. In some cases, projects returned to conventional methods after encountering difficulties. Blasting was still used. Manual excavation continued alongside mechanized systems. The transition was gradual, uneven, sometimes reversible, but this gradualness is often compressed into a more decisive storyline because it fits better. It creates clarity. It suggests direction, and clarity is easier to communicate than ambiguity. Even the image of the machine itself is simplified. In diagrams, it appears as a single unified object: a cutter head, a shield, a conveyor, all functioning together in perfect coordination. But in practice, the machine is a collection of subsystems, each with its own failure modes, each requiring maintenance, each interacting with the others in ways that are not always predictable. A small malfunction in one part can affect the entire operation: a sensor misreading pressure, a hydraulic seal degrading under heat, a misalignment in the thrust system. Individually, these are manageable. Together, they create a system that requires constant adjustment, and yet this ongoing adjustment is rarely part of the main narrative. Instead, the emphasis remains on the outcome: the completed tunnel, the finished infrastructure, the visible result, which leads to a broader pattern. The popular story focuses on endpoints. The technical record focuses on processes. And the difference between these two perspectives is not just a matter of detail. It changes how the machine is understood. Because when the process is examined closely, the machine no longer appears as a simple tool moving forward through the earth. It becomes something else: a system that operates within limits, a structure that depends on continuous human intervention, a machine that does not eliminate complexity, but reorganizes it into forms that are less visible from the outside. So the question is not whether the common narrative is incorrect. It is whether it is incomplete. Because if the technical details, the interruptions, the redistributed risks, and the gradual adoption all appear consistently in the historical record, why do they appear so faintly in the way the history of tunnel boring machines is usually told? At this point, the question shifts, not whether the story is accurate, but why this version of the story became dominant. Because the simplified narrative does not appear by accident. It aligns with several different interests: economic, political, and symbolic, without requiring any single coordinated intention. Start with scale. A modern tunnel boring machine can cost tens of millions of dollars to design, manufacture, and transport. Some of the largest machines, over 15 meters in diameter and weighing more than 1,500 tons, are not just tools. They are investments. And investments require justification. Large infrastructure projects depend on funding, public funding, private financing, international partnerships, and in each case, the project must be presented in a way that appears stable, predictable, and beneficial. A machine that advances at a steady rate of 10 meters per day is easier to explain than a system that alternates between rapid progress and extended pauses due to geological variability. A narrative of control is easier to communicate than a system built around adaptation. So the story becomes structured, linear, clear, because clarity supports confidence, and confidence supports funding. This does not mean that the technical complexity is hidden. It exists in reports, in planning documents, in engineering assessments. But these documents are not designed for broad audiences. They are written for specialists, for decision makers, for those already familiar with the constraints. The public-facing version of the story serves a different purpose. It simplifies, it emphasizes outcomes, it reduces uncertainty, and in doing so, it makes large-scale projects appear more manageable than they often are in practice. There is also a symbolic dimension. Machines like tunnel boring machines do not just build infrastructure. They represent capability. A country that can construct long tunnels through mountains or beneath urban centers demonstrates a form of technological maturity. It signals engineering competence, organizational capacity, control over complex environments. In this context, the machine becomes more than a technical object. It becomes a symbol of progress, of modernity, of the ability to reshape geography itself. And symbols tend to favor clarity over complexity because they are meant to be understood quickly, repeated easily, recognized widely. A narrative that includes interruptions, failures, and uncertainty is harder to turn into a symbol. It introduces ambiguity, and ambiguity weakens the message, so the story adjusts, not by removing facts, but by selecting which aspects are emphasized, which are repeated, which are left in the background. There is also an economic rhythm to consider. Construction projects operate under time constraints. Delays are costly. Every day a machine is idle, expenses continue. Labor, energy, equipment maintenance, financing costs, all accumulating even without forward progress. In this environment, the idea of continuous advancement is not just a narrative. It is a target, a goal that teams work toward, even if it cannot always be achieved. And over time, this goal begins to shape how the project is described. Success is measured in completed meters, schedules, deadlines met. The variability behind those numbers becomes secondary because it complicates the metric. In reports, the final output is often clear. A tunnel completed in a certain number of months, at a certain cost, with a certain capacity. These are the figures that circulate. These are the figures that are cited. And these figures reinforce the idea of efficiency. Even if the path to those numbers involved phases that were anything but efficient, there is also a historical pattern. Industrial technologies have often been framed as markers of progress. Railways, factories, power plants, each introduced new capabilities. Each reshaped economic and social systems, and each was eventually incorporated into a broader narrative of advancement. Tunnel boring machines fit into this pattern. They extend infrastructure. They enable connectivity. They support urban expansion, so they are placed within an existing framework. Machines move society forward, and once a technology is positioned within this framework, the narrative tends to stabilize. It becomes self-reinforcing. Educational materials repeat it. Media representations echo it. Public understanding aligns with it, not because alternative interpretations are impossible, but because the existing narrative is functional. It serves multiple purposes at once. It explains, it justifies, it symbolizes, and importantly, it does so without requiring detailed technical knowledge from the audience. The machine becomes understandable at a glance. A rotating cutter head, a tunnel forming behind it, forward movement, progress. But this functional clarity comes with a trade-off, because the aspects that do not fit neatly into this structure, interruption, adaptation, constraint, become less visible, not absent, but less emphasized, less repeated. less central, and over time, what is repeated becomes what is remembered, which leads to a subtle shift. The machine is no longer seen as a system operating within limits. It is seen as a solution that appears complete, reliable, predictable, even when the underlying documentation suggests something more complex. So the question becomes less about whether the simplified story is intentional, and more about how well it fits the needs of those who use it. Because if a narrative helps secure funding, communicate capability, and symbolize progress, it does not need to be entirely inaccurate to become dominant. It only needs to be useful, which raises a different kind of question. If the story we tell about this machine aligns so well with economic goals, political messaging, and symbolic representation, to what extent does it reflect the full reality described in the technical and historical record? If the broader narrative emphasizes clarity and outcome, the documents move in a different direction. They slow down, they record, they describe what happens when the machine does not behave as expected. And these records are not rare. They appear in engineering logs, maintenance reports, safety briefings, and post-project analyses. Not written to challenge the idea of progress, not written for public interpretation, but written to solve problems that occurred in real conditions. In these documents, the tunnel boring machine is not a symbol. It is a system under stress, a system that must be monitored continuously, adjusted constantly, and sometimes paused entirely. Consider the daily logs from tunneling operations. Each shift records measurable variables: cutter head rotation speed, torque levels, penetration rate, often just a few millimeters per revolution in hard rock, temperature readings from bearings and hydraulic systems, pressure at the tunnel face. These numbers do not tell a single story. They fluctuate. A machine that advances 12 meters in one day may only manage 2 meters the next, not because of inconsistency in operation, but because the material ahead changes. And when it changes, the response is immediate. Operators reduce thrust, adjust rotation speed, modify the balance between cutting and pressure. In some cases, they stop entirely. These pauses are documented with precision. Advance halted due to excessive cutter wear. High torque fluctuation detected. Water ingress observed at tunnel face. Each entry is specific, technical, focused on cause and response. And over time, a pattern forms. Progress is not continuous. It is conditional. Another type of document reveals a different aspect. Maintenance records. Here, the physical limits of the machine become visible. Cutter discs, made of hardened steel alloys, are designed to withstand extreme abrasion. And yet, in certain geological conditions, they degrade quickly. Edges dull, surfaces crack. In some cases, entire discs must be replaced after less than 200 meters of operation. Replacing a cutter is not a simple task. The cutter head must be secured. Systems must be shut down. Workers enter the front section of the machine, often through narrow access points. The space is confined. Visibility is limited. The surfaces are coated with a mixture of water and crushed rock. The weight of each cutter, sometimes over 100 kilograms, requires careful handling. This is not the image typically associated with mechanized efficiency. It is manual intervention inside a highly mechanized system, and it is routine. Safety reports add another layer. They do not describe large-scale disasters in most cases. Instead, they document smaller, repeated incidents, slips on wet surfaces, strain injuries during maintenance, exposure to high noise levels over extended periods. In pressurized tunneling environments, additional procedures appear. Workers entering high-pressure chambers must follow strict time limits. Decompression protocols are recorded. Delays occur not because of machine failure, but because human physiology imposes constraints on how long certain tasks can be performed. These constraints are not peripheral. They are integrated into the operation. They shape schedules. They define how and when maintenance can occur. But they are rarely emphasized outside technical contexts. Engineering reports written after project completion often reflect on these factors. They include sections on performance variation, on geological unpredictability, on equipment wear rates, on adjustments made during operation. The tone is analytical, measured. There is no attempt to dramatize, but also no attempt to simplify beyond what the data supports. And in these reports, the machine appears differently, not as a continuous forward force, but as part of a system that adapts in response to conditions, sometimes successfully, sometimes with difficulty. There are also economic records, cost breakdowns, time overruns, additional resources required to manage unexpected conditions. These figures do not contradict the value of the machine. Many projects are still completed faster and more efficiently than they would have been using earlier methods. But the path to that outcome includes variability, and that variability has measurable consequences. Extra days, additional labor, increased material consumption, all recorded, all accounted for. And yet, when these projects are summarized, the emphasis shifts again. Total length completed, final cost, completion date. The variability is compressed into a final number. The process becomes an endpoint, which creates a gap between what is recorded during the project and what is remembered after it, because the data was always there. In logs, in reports, in technical analyses, nothing was hidden, nothing was removed. But integration is something else. It requires connecting these details to the broader narrative, allowing them to shape how the machine is understood, not just how it is operated. And that rarely happens. Instead, the technical details remain where they are most useful. Inside documents, inside systems, inside professional contexts, while the broader story continues to emphasize clarity, continuity, progress. So the question is not whether the information exists. It does. It always has. The question is why it so rarely becomes central to the way the history of tunnel boring machines is told. When the story is removed, the machine does not disappear. It is still there. Steel, weight, motion. A cutter head turning slowly against rock, advancing a few millimeters with each rotation. A system that requires constant input, constant monitoring, constant adjustment. What changes is not the machine, but the certainty around it. Because without the simplified narrative, the idea of smooth, uninterrupted progress becomes harder to maintain. The tunnel is still built, the infrastructure still exists, but the path that led to it no longer appears linear. Instead, it looks segmented. Phases of advancement, phases of interruption, moments where the machine adapts, moments where it cannot, and in between decisions. Human decisions, adjusting parameters, responding to data, working within constraints that are not always visible from the outside. The machine, in this view, is not a final solution. It is part of an ongoing negotiation between design and environment, between expectation and condition, between what is planned and what is encountered underground. This does not reduce its significance. If anything, it makes it more precise, because the machine's value is no longer based on an idealized version of constant efficiency, but on its ability to operate within limits, to function in conditions that are unstable, variable, and sometimes resistant, and to do so through a combination of mechanical force and human intervention. At the same time, some things become less certain. The idea that technological development follows a clear, continuous path. The assumption that increased complexity always leads to reduced risk. The belief that systems become fully predictable once they are engineered. These assumptions are not entirely false, but they are no longer complete, because the details suggest something else. That complexity does not disappear. It changes form. That risk is not eliminated. It is redistributed. That predictability is not absolute. It is conditional, dependent on factors that extend beyond the machine itself, and many of these factors remain outside complete control. Geology, material variation, wear over time, human limits, all interacting with the system designed to move forward, and often succeeding, but not always in the way the simplified story implies. So what remains is not a replacement narrative, not a correction that overturns everything that came before, but a different perspective, one that allows multiple layers to exist at the same time. The machine is progress, and the machine is process. The machine is capability, and the machine is constraint, both visible, both supported by evidence, but not equally emphasized. Which brings the focus back to the act of telling the story itself. Because the way a machine is described does not only reflect what it does, it reflects what is selected, what is repeated, what is considered central, and what is left in the background. For decades, the tunnel boring machine has been presented as a clear example of technological advancement. And in many ways it is. But when the details are placed back into view, that clarity becomes more complex, more conditional, less absolute, and perhaps more accurate. So the question is not whether the original story should be rejected. It is whether it is sufficient. Because if for so long we accepted such an orderly story of technology, how many other histories are we still repeating simply because they fit better into the narrative of progress?